Welcome, everyone. I'm Anjana Srivastav. I head our partner enablement globally for Dataiku, and I am joined here by William Benton, who's a principal product architect at NVIDIA. And we are super excited, William, to talk to you today about how we can jointly achieve the goal of building accelerated data science applications using Dataiku and NVIDIA together. So over to you, Will. Talk to us more about what do we even mean by accelerated data science?
Thanks, Vinay. Accelerated data science. I want to start by sort of talking about the history of data science, how we sort of got to where we are, and what a day in the life of a data scientist looks like. And this will be familiar to those of you who are Dataiku users because you go through a similar process as you're developing recipes and projects. 10 years ago, data science was really a full stack role where you were responsible for everything on the slide, from sort of identifying whether or not there was a business problem to solve with your data, identifying how you would solve it, finding the sources of data that you need, collecting them, putting them together, and then all the way over to sort of training a model to exploit structure in that data and using that data to provide a report to stakeholders. Now, I have on the top half of this diagram sort of production deployment and continuous validation and monitoring, which you'd see if you were putting a model into an application. But 10 years ago, people weren't putting models into applications all that often. People were really using models to inform something they did with the business. And because a lot of the focus of data science in this era was on processing data at scale, we're going to collect all the digital exhaust from our enterprise and do something meaningful with it. Then we really focused on compute skills, right? And data scientists largely came at it from a computing or a statistics background, but computing was a big part of the role. And the tools that a data scientist had in this era were sort of targeted towards things that you could execute on a large compute cluster and that were easy to use responsibly, even if you weren't a specialist statistician. So we had a lot of techniques that were easy to scale out, that produced pretty good results, and that would work, on your large data sets. Now, today, data science is a specialized role. A lot of data scientists don't come at the discipline from a computing background. They come at it from a quantitative background. Maybe they were an economist or a social scientist. Maybe they were a physicist or a mathematician or a statistician. They have access to a toolbox of more sophisticated techniques, and they're not as concerned with this entire end-to-end workflow as a data scientist would have been in 2014. And we see a focus really on this inner loop of extracting features from data, finding a model to exploit that structure, and making sure that our model is something we can use responsibly in production while handing that off to an ML engineering team to do the actual production deployment. And all of the tools that we cared about before are still important to data scientists today, but they have a new toolbox of more sophisticated techniques, many of which depend on accelerated computing. Things like really doing advanced analytics on huge data sets, things like instead of hashing a feature, coming up with an embedding to put features in a semantic space, learning manifolds that depend on nonlinear techniques, deep learning frameworks like PyTorch, JAX, and TensorFlow, using AutoML, where you run a whole lot of experiments all at once to automatically search the space of possible techniques to solve a problem. We've also seen, as machine learning goes more into production, we've seen an increased emphasis on explainability and interpretability of results. So if you have a machine learning model, it's not enough to say that this model performs well. You need to be able to talk about why it does what it does. And finally, large language models, obviously a huge hot topic, right? Large language models are an important part of many of today's AI applications, but they really also underlie this entire workflow. I know a lot of people who can't imagine going back to writing code without an LLM assistant helping them along. And I find that even if I'm debugging something, chatting with an LLM is sort of like chatting with a colleague. I work remotely, so I can't just walk over to someone's cube, but I can explain to an LLM what I'm doing wrong in my code and sort of get some insight from just even putting it into words and getting feedback. So we have a whole lot of techniques. We have data scientists who don't care about compute. But what does it mean for acceleration? Well, for some of these techniques, it means that you can actually use them at all, like large language models, AutoML, deep learning, and manifold learning. But acceleration can mean a lot of different things to different people. And what you get out of acceleration is going to depend on your business. So it may mean using the same technique on a larger data set or on your entire data set without sampling it at all. It may mean that if you have a batch job, you can meet a tighter SLA, or you can achieve higher throughput for production inference. It may mean considering more dimensions of a problem using a more sophisticated technique, going from a sort of flat plane to a cube, for example. And it may mean solving the same problem with less money, less power, or fewer computers. So acceleration can mean not only that we improve our total cost of ownership for compute infrastructure, but it can also make our compute infrastructure more environmentally friendly because we're using less power, we're using less cooling, we're using less space in a data center. Finally, acceleration can have immediate human impact by giving practitioners a larger toolbox of feasible techniques, but also a larger toolbox of techniques that are suitable for interactive use. And if you think about the creative part of your job where you're sort of getting into a flow state, this is where this is really interesting. And I think this is one of the greatest advantages of acceleration for data science. So to see why, though, I want us to go back even further than that 10 years ago when we were talking about the history of data science. And I want us to think about sort of the very early history of human-computer interaction research. If we go back a little more than 4 decades to 1982, we see a foundational human-computer interactions study from Doherty and Tadani at IBM Research. And they were investigating how time-sharing sort of mainframe systems worked and how people worked with these systems. And in the past, the conventional wisdom had been, hey, as long as you return an answer to the user within a couple of seconds, the user's going to be fine, right? And what Doherty and Tadani realized is that actually they didn't identify a limit at which the computer was too fast to make a difference, right? As the computer kept getting faster, the human interacting with the computer didn't get distracted, stayed in that flow state, and was able to issue new commands to the computer even faster. So you had a virtuous cycle where you had a more than linear speed up. We can see what this looks like. They only tested down to 400 milliseconds, but they really didn't identify this phenomenon dropping off at all. As we decrease the amount of time that the computer takes to respond, the human becomes faster as well. And so we can see that this actually reduces. And then as the human time decreases, the overall latency of the system improves. Now, this was true in 1982 on a time-sharing system where you're typing green letters on a black terminal, but it's also true in 2024 when you're typing a recipe into a Jupyter notebook. And if you're using a platform like Dataiku, where the goal is to come up with a great technique to identify something that your business hasn't seen yet, or to solve a problem that you need to solve, and you're going to iterate on a lot of techniques, and you're going to need to explore these things. You're going to need to stay in that flow state, right? And you have a lot more distractions on your computer than were available in that terminal in 1982, right? So staying in that flow state is really important. And identifying how to do these techniques at low latency really depends on accelerated computing. But remember that our practitioners today aren't the kinds of people who think, hey, it would be really fun to implement a parallel version of naive Bayes so that I can run it on my Hadoop cluster. They're people who've come from a quantitative background and are just not interested in thinking about computing except as a tool, right? This is a tool, not something that I want to build myself. So to that end, let's talk about the enterprise frameworks that NVIDIA has made available to meet data scientists where they are that you can integrate in your Dataiku workflows. The first one is NVIDIA Rapids, which is a set of libraries for exploratory data science development and production data science. And these provide the power and performance of accelerated computing behind familiar interfaces. So if you're a data scientist, you've probably used pandas or polars. Well, you can use cuDF to accelerate both of those libraries. You've probably used scikit-learn to train a machine learning model. cuML provides accelerated implementations of scikit-learn. And in many cases, you can use these libraries with pandas, polars, or scikit-learn without any code changes at all. Similarly, cuGraph is an accelerated version of NetworkX. And there's integration with ecosystem libraries like Plotly and the training frameworks in XGBoost. Now, if you can't run your problem on a single node, you might need to scale out. If you have too much data to fit in memory, you're going to use something like Dask to scale that out or to operate on larger data set sizes. If you're using Apache Spark for processing data frames, doing analytic processing, well, you can also scale out those workloads using the Rapids Accelerator for Apache Spark, which uses the cuDF library to accelerate data frame operations transparently to the user. So you can see a lot of big speedups with these accelerated data frame processing techniques. So let's look at some examples of some of these new techniques that data scientists care about today and see how much faster they are. So a nonlinear dimensionality reduction technique like UMAP, which we've pictured on the right, can really help you identify structure in a data set when you're exploring it for the first time, better than a technique like PCA came on the left. Here I've just sort of naively applied these techniques to the same data set. And I think the picture on the right makes it clear that, yeah, there's some structure we could learn here in this data set. The picture on the left doesn't, but they took about the same amount of time to generate because I used accelerated computing for the UMAP. So in an interactive context, you might be restricted to using something like PCA if you don't have accelerated data science. But if you do have accelerated computing with Rapids, and you can do something like on the right, which will get you a better result. And this is often more than 100 times faster for realistic data sets. And often it makes it practical to use on data sets that you wouldn't even consider without acceleration. Another thing we can look at is calculating feature importances with SHAP. And this is basically for every prediction, how much did each feature contribute to the result? And for this problem, I'm looking at a data set that has 7.5 million rows, 9 features. I'm running this on my workstation. So in your data center, you probably have access to more powerful GPUs. In the public cloud, you have access to more powerful GPUs. But if I wanted to calculate feature importances with SHAP for every example, it took me 16.5 seconds on the GPU. If I was going to do this on the CPU, I had to sample down to 10% of my data set. And even with 64 threads on my CPU, it took me 24.5 seconds. So a single GPU was able to calculate these feature importances for 10 times as many features, 1.5 times as fast. It's 15 times more throughput than we would see with the CPU. This advantage becomes even more pronounced if we look at calculating the importances of feature interactions. Again, if we compare a 64-thread CPU to a single workstation GPU, and we look at a smaller number of records, say we look at 750,000, the CPU takes 8 minutes of wall time, but 8.25 hours of CPU time. So if you have fewer threads in your CPU, divide that out. The GPU finishes this task in 7.25 seconds, or over 65 times faster in terms of wall clock time. Now, analytics is an important part of a lot of data science workflows as well. You may use Spark in your workloads. In this case, we're looking at 103 analytic queries from a hypothetical retail application. These are the kinds of things you might be running in a recipe. You may be running these as an analyst and waiting for a result to think about what you're going to do next. The overall speed up in these queries was 7 times if we ran all 103 end to end for running on the GPU rather than on the CPU. And if we look at this cumulative distribution, we can see that about 35% of these queries accelerated more than 4 times, and 20% of these queries accelerated more than 6 times. Now, obviously, this is going to be workload dependent because this is transparent to the user. There's no code changes necessary to get these acceleration. But you can see that for a lot of workloads, this is a huge benefit. And especially if you're sitting around waiting for a result in a window, you want this kind of speed up so that you can stay in the zone. Also, large language models are really exciting, right? Whether you're using those as a coding assistant, whether you're using those as a component in a retrieval augmented generation pipeline, whether you're using those to build another application, right? Or generate synthetic data. And you want to run these things sometimes on your own infrastructure. You may have data that you want to control, and just pulling down a Docker container from the internet and a model from Hugging Face is not necessarily something that you want to do in a production context as an enterprise. NVIDIA NIM brings you enterprise grade accelerated generative AI inference on any footprint, whether you have GPUs in your data center, on the public cloud. And what we're doing is we're packaging up a hardened enterprise ready model container with a Helm chart so you can deploy it on Kubernetes. We support the same APIs that the model endpoints you're using in the public cloud or from third-party providers are already using. So these integrate seamlessly into your application. You can customize an NVIDIA LLM with parameter efficient fine tuning or even your own fully custom models. And finally, we've done a lot of hard work to optimize these engines for NVIDIA GPUs. So you'll get the best possible performance and throughput, which means that you can serve more customers with fewer resources, serve more clients with fewer resources, and really realize more return on your investment in AI. So now I want to turn it over to Anjane. We'll talk about how we can see these integrated into LLM Mesh and see the accelerated data science tools that I talked about earlier integrated into your overall Dataiku workflow. So I want to hand it over to Anjane at this point so you can see how these benefits concretely are made available to you through Dataiku. We're really excited about how these things can accelerate your workflow.
Amazing, William. I mean, you covered all the way from the data prep side of the analytics to the generic machine learning and data science to, generative AI. And, now let's try and put Dataiku in that framework and look at what solutions, features, capability does Dataiku offers to accelerate some of these data science workflows with NVIDIA. So one of the things that I would like to say is that Dataiku is a unified collaborative platform that allows user from all the personas, whether low code, no code, or full code personas, whether you're a data analyst or a data scientist, collaboratively in one single space. When we talk about the GPUs, there might be some applications in the data analyst persona where GPUs might be used, but primarily we are talking here about the data scientists. And within data scientists, we can also apply the 80-20 rule. There's a whole spectrum of data scientists that go from people who can write very sophisticated SQL queries to people who can really code models and deploy them at scale in production to do machine learning at scale. So Dataiku is primarily here to reduce the barrier of entry of those 80% of the data scientists primarily, to Will's point earlier, who might not be interested in really figuring out how to set up the compute, how to do Docker setups and all that fun stuff. So I'm going to showcase here and talk about some of those features and capabilities that really fast tracks those data scientists who are willing to use the GPU technology, but there are certain barriers of entry that coding presents that is stopping them from using the full power of the software libraries and the hardware that NVIDIA provides. So this is a sample architecture of how Dataiku acts as that orchestration layer, pushing down the compute and leveraging the compute of NVIDIA technology across the stage of a data science application. So if you talk about initial data prep steps, as well showed how leveraging Rapid Spark can really make your analytics workflows, data pipelines go 7 times faster, which is great. Dataiku allows you to build those data prep steps in a low code, no code way, and then push it down to leverage NVIDIA Sparks without a Rapid Spark, without really writing any lines of code. Then we talked about the Rapids ML library. And the Rapids ML library are a great way to leverage the CUDA layer under the hood that is optimized to further use GPUs at speed under the hood as the hardware. Dataiku provides you a way to minimalistically write 2 or 3 lines of code and then leverage the power of Rapids ML in terms of model training, but then still maintain the GUI features that Dataiku provides to explain and interpret those models that you're training using RapidsML. In addition, I have before getting into this role, I was a data scientist for 10 plus years. Every single time I have to set up a code environment for my team members, I have to do it on individual PCs, or now with Kubernetes, I can do it in a common cluster. But still, you need every single time a new data scientist has to be onboarded, you need to figure out that the environment stays consistent across those data scientists. Dataiku has those abilities to set up those code environments one, and then as soon as a user onboards on that platform, they're working off of the same environment. And then lastly, we're talking about generative AI, right? NVIDIA has come up with this great framework of NIMs that allows you to build Gen AI applications from soup to nuts, from model training to model inferencing, all packaged in single Dockers. But in order to really leverage that power, data scientists still have to write some code. So that's where enters Dataiku to provide you that GUI-based interface, where once you set up that NVIDIA NIM into the Dataiku instance in a low-code, no-code way, your end users can just start chatting with it and start building Gen AI applications with it. In addition to that, we have some of the common pipelines created where we can leverage NVIDIA's pre-trained models like Monai and convert them into plugins so that your end user can leverage all that power that NVIDIA's pre-packaged models provide in terms of image classification in case of Monai without really writing code. So you sense the theme here. Cool. So let's go and look at a demo here. This is a sample workflow of how this all comes together. Let's see this in an action in Dataiku. So as I talked about in Dataiku, the first thing we are talking about is data prep, right? So in data prep, the feature and the capability that we provide is visual, no-code, low-code recipes to do data prep. And then I'll show you how we can do that with RapidSpark. So in Dataiku, if you go to the administrations tab, this is a one-time setup that anyone has to do. We have options available to set up your compute and scaling infrastructure. So we're talking about Spark here. So as you can see in Spark, you can have your basic CPU configurations with your Spark executor memory, number of partitions, blah, blah, blah. But then in addition, you can also create configuration that specifically runs the RapidSpark. Here you would add the features like how many number of cores you want, the GPU nodes that are available. You would set up a Spark plugin, which is a jar file that allows Dataiku users to leverage RapidSpark in a low-code, no-code way. But once this setup is done by an admin, that's it, you're done. So now, if I go and see how a user is actually experiencing this, I am a financial analyst or a data scientist in the finance team who's trying to predict credit card fraud. I have transactions, and these transactions are in the order of millions and millions of transactions, tens of millions of transactions coming in every day, and I want to do a bunch of data prep with them. So I will go and look at these transactions, and I'll probably create some date transformations, some geocoding that I might need for my machine learning model. Once I create these prep steps, one of these hundreds of prep processors that we have available, I want to execute this. And Dataiku's biggest value proposition is leverage the compute that is available to you. So we use the engine here as the Spark engine. So as an end user, as a data scientist in the finance team for a big bank, I just say, okay, I want to do all of this data prep, run this for me on Spark. One of the things that I would change pretty quickly is the Spark config. So instead of using my default CPU-based Spark config, I select the Spark Rapids config. And now without doing any coding, I am leveraging all the goodness of Spark Rapids. and we are getting the value gains that William showed you earlier of using Spark Rapids on large data sets versus CPUs. The second thing is we did some data prep. Great. We have the data prepared. Now I'm ready to do some machine learning. Love it. In order to do machine learning, I here set up a code environment. So, okay, I'm my lead data scientist. I love working with Rapids libraries from NVIDIA. I set up a Rapids environment as a code environment here. I install some of the packages that I need, which are the QDF and the QML packages that I need to run my machine learning models. And that's it. Once I've set this up, let's look at how the experience is going to be for the end user. So again, going back to my credit card prediction model, I'm going to go and look at the machine learning models that have been trained. So I can go and train a whole bunch of CPU-based models like random forest, gradient boosting, but I can also try to use these models with GPUs. But then I want to try Rapid Spark. So we have this widget called custom Python model, where you can go and just write 2 lines of code where you initialize your random forest classifier. You set up the parameters of the random forest classifier, and that's it. You hit the train button. Once you do that, you have all these models trained and available. So you can see I am comparing machine learning models built by random forest, which is giving me an 80% AUC, versus the custom Python model, which was the Spark Rapids, which is giving me a better AUC. Now, not just this, I can go and look at this model, and I have all the good things like computing the feature independence, feature importance, subpopulation analysis. I can go and look at the confusion matrix. I didn't write a single line of code. In my past life, I've written thousands and thousands of lines of code just to figure out what's the threshold should be to get to the right recall. And then the last thing that I would present here is we talked a lot about NIMs. Generative AI is the rage these days. NVIDIA NIMs is the way to do it. So let's see, how do we set that up in Dataiku? So in Dataiku, we go again to our favorite admin panel. We go to connections. In connections, when you go to new connection, Dataiku offers you ways to connect to different SQL sources. But during the course of all these sessions in our product days, you'll hear a lot about our LLM mesh and all the goodness that LLM mesh provides, which is acting as the backbone to build generative AI applications. We are going to go and add a custom LLM. So in the custom LLM section, Dataiku has created an NVIDIA NIM plugin. What does this NVIDIA NIM plugin allows you to do? This NVIDIA NIM plugin allows you to add generative AI models or LLM models that are made available in some of those NIM packages. So here I want to do a text completion capability, and I want to use, let's say, a gamma model. Once I select that and set this, these NIMs will be available for prompt engineering for an end user. Not only that, I can set a whole bunch of parameters here. For example, all my prompt queries need to be audited. So I can save the metadata, and I can see the responses, and I can create a whole feedback loop by looking at the responses if they were good or bad. I can create security guardrails in terms of adding forbidden terms, doing some toxicity detection, PI detection, all this goodness without writing a single line of code. Once I set up this configuration, let's see how this NVIDIA model is available for an end user. So for an end user, Dataiku provides you four or five sort of LLM recipes to harness the power of generative AI. So you can think about as step one, I simply do some classification or summarization. Step two, I'm doing prompt engineering. Step three, I'm adding RAG. I'm creating RAGs by adding my own data to the LLM APIs. And then step five, I'm actually doing fine tuning. So in each of these steps, you're using some LLM. So I can go in my step one, where I'm doing a basic simple classification. And here I can use my NVIDIA NIM models to classify a bunch of text. Or I can simply go and create prompts. I can select my NVIDIA NIM model, which is a meta model, and I can start asking it questions around my business. So this was a quick and short demo around how do Dataiku provides capabilities essentially to leverage the software libraries and the hardware that NVIDIA provides, and really reduces the barrier of entry for any data scientist to adopt and consume these NVIDIA technologies. Any questions? This was a lot of fun for me, Will. I hope this was good for you as
Likewise.
well.
Yeah.
But yeah, thank you for tuning in.